This lesson is for FST lesson 11.3 on other normal distributions. Most of what we're going to talk about today is related to this yellow box, the standardization theorem. Students do need to memorize it by name. It's basically turning any score into a z-score. Z-scores were studied earlier in this course, and the way that you calculate a z-score is you take your piece of data, the x value, you take away from it the mean or the mu, and you divide by the standard deviation. Once you've turned your score or your data into a z-score, then it can be easily put onto the standard normal curve, and you can use either the table or the normal CDF command on your calculator to calculate probabilities. Some other information about the standardization theorem: the process of getting a z-value from the original data is basically you're applying a transformation of the original data onto a z-score. That process is referred to as standardizing or standardization. So if students are familiar with a standardized test, it's because your scores have been converted into a z-score and put it into a standard normal curve. When you standardize the domain of a normal distribution, you can determine probabilities then by using the processes we learned back in lesson 11.2. Be careful though, the standardization theorem only applies to sets of raw data that are normally distributed. Your hint here for when to use this process is basically the word problem will have to state that the data is normally distributed. That will have to be spoken or said somewhere in the wording. Z-score transformations of data will preserve the shape of the raw data distribution. However, if that original distribution isn't normal, then the z-scores won't matter because they won't provide a standard normal distribution, even if the mean is 0 and the standard deviation is 1. So you have to look for that statement somewhere in the wording, and then you can convert it to a z-score. Let's do an example. This is example 1 in your book. They ask you to refer back to page 698, so I took the information from that page and I put it here for us. An adult Dutch male is selected randomly. What is the probability that the man is less than 188 centimeters tall? We did a question similar to this in a previous lesson, so that's where this data comes from. Notice that it says heights of adult men in the Netherlands are approximately normally distributed. If they don't mention that, then there's no point in converting it to a z-score because it wouldn't be part of the standard normal distribution. They tell us that the mean is 183. They tell us that the standard deviation is 6.7. So we're going to take the piece of data that they did give us, the 188, and we're going to turn it into a z-score. The way that we do that is we subtract the mean and then we divide by the standard deviation. Be careful when you type this in. If you just type it in as 188 minus 183 and then hit the divide key, your calculator is smarter than you in this case. It will divide first and then subtract. So if you're doing it in one swoop like this, you'll either need to put parentheses around it, or what I would recommend, do it in 2 steps rather than 1. Subtract, hit enter, and then divide. And so when you do that, you get 0.74626. Now I want to talk about rounding for a moment. Rounding is a key skill in math class. If we rounded this to the hundredths, the 6 would be the deciding digit. The 6 would round the 4 up. If we were rounding to the 10th, it would just be 0.7 because the 4 is the determining factor and the 4 says don't round the 7 up. So if we were rounding to the 10th, we'd say 0.7. If we were rounding to the 100th, we'd say 0.75. I want to clarify rounding to the 10th here. If you round to the 10th, the 4 is the deciding digit. The fact that the 6 would round the 4 up is irrelevant. 4 is the deciding factor, and so the other pieces there don't even exist. So the 4 isn't larger than 5, so we don't round up in that case. We are going to round to the hundredths here. So we're going to go to 4, 6. The 6 would tell us we do round up to the 4 here. The 4 will change, so our answer here is going to be about 0.75. So that number is a z-score. So if we place that number on the standard normal curve, we are above the mean because the mean on the standard normal curve is 0. We're 0.75 above that. So we're not quite to 1 standard deviation, but clearly we are above the average because the average is 183 and we're above that at 188. So we're not quite to 1 standard deviation above, which makes sense because 183 plus 6 is going to be bigger than where we are. So we're not quite to 1 standard deviation. If you look up 0.75 in the table, which I'll show you shortly, you're going to get the answer for how much space is covered from that z-score and back. So everything prior to that number. So we're looking at how much space is taken up or how much area is covered from negative infinity up to this point. So let's look at the chart and see if we can figure it out from there. We got this chart back in 11.2. It's also available in your textbook. So we're going to go to 0.75. So 0.7, and then we're going to go over to the 5. So I've already got that one circled for us. It's 0.7734. So 0.75 is right here, 0.7734. So the z-score was 0.75. That's not my final answer. When I looked up 0.75, I got 0.7734, and that's my final answer. That's the probability that a man is less than 188 centimeters tall. Know that you could have also done the normal CDF command on your calculator. You would have gone from negative infinity to 0.75. You'd keep the 0 and the 1 as your mean and standard deviation because this is a standard normal curve now that you turned it into a 0.75. When you do that, you should get exactly the same answer. So that's the basics of what we're doing in this lesson. You are converting scores into a z-score, and then you're using the table or your calculator to calculate further from there. Let's look at example 2. And what I like about example 2 is it's kind of a real-life example that you can actually relate to. I don't know that any of you are ever going to work at a place that fills bags with popcorn, but we all have probably eaten a bag of popcorn before, so we can at least relate in that sense. So let's read what it says. A machine fills bags with popcorn. So they are doing this at the factory. If the bags are underfilled, there will be complaints from the consumer. I paid for my bag of popcorn, but I didn't get very much product. And I'm sure that does happen quite often. If the bags are overfilled, then they can't be closed and sealed properly in the production line. That would be problematic because then they can't sell them. The bag states that there are 7 ounces in the bag, so 7 ounces of product. The company has chosen to fill each bag with 8 ounces of popcorn on average. Assume the quantity of popcorn in each bag is normally distributed with a standard deviation of 0.6 ounces. So first let's calculate what percent of the bags are likely to be under the stated weight of 7 ounces. So what are the chances that when you buy your bag you're not going to get what they say? So we're going to first take that 7-ounce bag and we're going to convert it to a z-score. The way that you do that is you take the piece of data, the 7, take away the mean, and divide by the standard deviation. When we do that calculation, we get negative 1.6 repeating. We expected to get a negative number because 7 is below the average. Numbers that are below the average will be negative, below 0. So now we need to figure out what it is that we're calculating when we look that number up in the table or when we calculate it on the calculator. First of all, let's draw where negative 1.6 is and figure out which part of the graph we're looking for. Negative 1.6 repeating is going to be to the left of the 0, and we're looking for everything under that, so everything below that number. So that's why I shaded in the small tail here to the left. Now, using the table, we're not going to be able to look that up because the table doesn't have anything below 0. So what we're going to do is look up positive 1.6 repeating in the table, and that's going to give us the big area here. So let's look that up. If I go to 1.66, because that's 1.6 repeating, we're not rounding here, we're just cutting off the number. So 1.66 is going to be right here at 0.9515. So the area from 1.6 repeating and lower is 0.9515. I'm going to find the complement of that because the complement of that is the same size as the tail that I'm really looking for. So I do 1 minus that number and I get the answer for less than negative 1.6 repeating. So I'd say about 4% or about 5% depending upon how you round. But for for our sake here, I'd like you just to keep the answer as a decimal. So don't do any rounding or changing to any percentages here. When you're speaking your answer, you can say about 5%, but you want to be exact here, and so avoid any rounding if at all possible. Another thing that I want to point out here is that you could type this in on your calculator and not have to worry about the table at all. You could do the normal CDF command, and you could go from negative infinity to negative 1.6 repeating. Be careful here in that you do want to be accurate. You don't want to just type in a bunch of 0.6s here by hand. You'd want to actually type it in as negative 1 2/3, or negative 5/3 would be another way to get that repeating decimal. And then the 0 and the 1 should stay. And in that case, you would still get the same answer. So I went ahead and actually calculated this using my calculator using the negative 5/3. So I do get a slightly different answer, and I believe it's because of the rounding issue. This one uses the repeating decimal exactly. This one we rounded to 1.66, so it's going to be off slightly, but not enough to make any kind of a huge difference. Let's look at the next question. Part B, if a manager purchases empty bags that can hold 10 ounces fully filled, then what proportion would be filled over the capacity? So that doesn't mean that they're necessarily filling them to 10 ounces altogether. On average, they're just wondering what would be the likelihood that that would happen. So we're going to convert the 10 to the z-score. So we do the same thing that we did with the 7, only now it's with a 10. And now we're going to get a positive number. We get 3.3 repeating. Or in improper fraction form, that would be 10/3. So that way we won't have to worry about the repeating decimal there. So let's look at what that actually looks like in picture form. So if we're at 3.3 repeating, we're above the mean of 0, and we're looking for anything over and above that. So we're looking for above 3.3 repeating, which is the tail to the right. If I look up 3.33 in the chart, you'll find that that doesn't exist. The chart only goes to 3.03. That's the biggest we could get to. So you would have to use a calculator on this one. So you're going to have to go to the normal CDF command, and you're going to have to get it to do 3.3 repeating, or 10/3, and then with 0 and 1. When you calculate that there, you get 0.999566. But again, remember that's the big area that we're not looking for, where we're looking for the complement of that, which is the tail up above it. So we do 1 minus that answer to get our final result. And that number is what we would expect. It's super small, because anything above 3 standard deviations above the mean, there's very little wiggle room there in our graph. Most of the data is between -3 and 3 standard deviations. So if we're 3 1/3 above the mean, we're well above it, and there's going to be very few possibilities there. On the next one, we're looking for what proportions of bags would contain between 7 and 10 ounces. What I like about this question is it combines your knowledge from parts A and B. At 7 is what we calculated from part A, below 7 is what we calculated from part A, and above 10 is what we calculated for part B. So if we add A and B together and do the complement of that, we'll get what's in between. Let me show it to you visually. Negative 1.6 was the z-value for 7, and we found everything below that for part A. For part B, we did everything for the z-value of 3.3 repeating for the 10, and we got everything above that. So if we add the parts that we already did in part A and B together, that'll be the two tails combined. The rest of the graph is what I'm looking for, though, for my answer. So I would do 1 minus part A plus part B, and that'll tell me what's left, which would be what's in between 7 and 10. Another way you could do this question is using your calculator. You could just tell it, instead of the lower bound being negative infinity, you could just tell it go from 7 to 10 with a 0 and a 1, and it should give you the same answer. And be real clear here, on the normal CDF, make sure you're using your z-values here, your z-scores. So instead of doing 7 to 10, you want to make sure to do negative 1.6 repeating as your lower bound and 3.3 repeating as your upper bound. And when I calculated that on the calculator, I got a slightly different answer, but again, remember we had already rounded for the 7 and the 10. So we got about 0.9518 when I did it on the calculator. When I calculated it using my answers from A and B, I got 0.9511. So very similar answers, close enough as far as I'm concerned. Students should be comfortable with problems like A, B, and C. Those are fair game for all quizzes and tests. The final question I want to look at with you today is part D of this example. Let's read through it and then we'll talk through the work that's shown here. If a manager decides that at most 1% of the bag should be overfilled, then what should be the capacity of the bag used in the packaging process? This time they give us the percentage, and we need to go backwards and figure out what the z-score would be. We still have the average of 8 and the standard deviation of 6, but we don't know what the z-score is. We do know that we want anything above 0.01, but we don't know where that z-score is that would make that happen. So we're going to look up 0.99 because that's the complement of what we're looking for, and we're going to find what the z-score is that matches with that. So we're going to use the table in reverse this time. This time you're going to look for 0.9900, and you're going to look for that in this region here. So look for 0.9900. And we'll have to scroll down here to see it actually on the video. So it looks like 0.9901 is as close as we're going to be able to get. And that comes from the z-score of 2.33. This is column 3 here. So 2.33 is our z-score that gives us the percentage that we're looking for. So let's fill that in. 2.33 is as close as we can get. That's the z-score that we're looking for, and we want to know what ounce bag that would be. So now we solve this equation for x. First you're going to multiply on both sides by 0.6. That's going to give you a new value over here on the right. On the left, we'll still need to add 8 to both sides, and when I round that to the 10th, I get about 9.4. This is a bag of ounces, so we'd say about 9.4 ounces. So this one's different from the ones we had done earlier because this time you have to find the z-score by going backwards in the chart. Finally, students need to make sure to read page 702 and look at book example number 3.